Let me actually. Do something else here. Now you have also permission to share screen if you need to. What's happening to Chul Hee? Anyway, I'm gonna put a whiteboard on. So are there any questions about chapter 6 so far?
You mean section 6 or chapter 6? Because I've not read chapter 6.
You have not read chapter 6?
Is it? I thought you said it was not section 6.
No, it was chapter 6.
Oops.
Starting at 262. So that it's, let me just, so this is, and so,
Professor, I think there is something wrong with your mic because I can't hear you once in a while. You like zone out. I don't know if it's happening for everyone else as well.
can you hear me now?
Yes.
So we're looking at measure spaces. And that's basically, we have a space X, could be finite dimensional or infinite dimensional. And on that space X, we have a collection of subsets M. And so first, M is a collection of subsets. Which is not empty, first of all. And it's closed under complements.
Professor, what page you are explaining? Absolute major theory is what page?
263 right now. And countable unions and intersections. So this thing is called a sigma algebra. And second, mu is a map from M to the extended positive reals. So it assigns to each subset, which is in the sigma algebra, a number. And then the triple X, M, and mu is called a measure space. So the more, if you give, I want to give a couple of examples. The first is I take X to be the integers, and I take mu of any subset of the integers to be just the element, the number of elements in S.
So is this the counting measure?
That's the counting measure. So S is a subset the integers. Now it has the right property. First of all, the power set of the integers is clearly a sigma algebra. Because it's closed under complements and under countable unions and intersection. Secondly, mu has to be sigma additive, meaning if En is a countable collection of subsets, where En intersected Ek is empty if n is not equal to k. So a countable collection of disjoint sub measure of union of the En is just the summation of the measures of En. And if you look at number of elements of S, that clearly all that holds. So this is X, well, C, the triple C, power set of C, and mu is a measure space. Okay, now let me go to the next page here. So I could also look at the triple C, power set of C, and let me call this mu prime. That's a different measure, where if S is a subset of C, then the measure of S is the summation over all K in S of 1 over K squared.
So this
Now
is the
we know
factor
that,
over K.
right? So we actually weigh each point in K in Z with 1 over its absolute value squared. We know then in this case, mu prime of the entire space would be in Z 1 over K squared, K not equal to 0. So we have to make a special case for 0 here, right? And so we give 0 just the measure 0. And this is just pi squared over 4, which we can compute, which would make the measure of the entire space finite. And then if we look at mu prime of C is equal to 4 over pi squared times mu prime of C, this is still a measure, has all the properties, but now we have mu double prime of the entire space, mu double prime of is equal to 1. In this situation, it's a probability measure.
Professor, I thought it was a pi square over 6.
Yeah, this would be a 3.
Oh, 6.
No, it would be a 3 because we go over the negative and the positive integers.
Oh, I see, I see.
So this would be what we call a probability measure.
Uh-huh. So it's like a normalization factor, right?
That's a normalization vector. That's if you have the entire space has finite measure, you can always do that.
Mm.
If it has infinite measure, you
Mm.
can't necessarily do that.
Mm.
But then you could, you know, do something like the probability mu double prime of the set consisting of 2 and 4 you can compute is now 3 over pi squared times a quarter plus 1/16, right? For any set, you can compute that. And I have a dog speaking up in the background.
Yes.
She's very opinionated.
I think she likes the counting measure.
Right. It sounds more like dislike. Okay, so now the other example, which is sort of important.
The integration gives a rise to a measure.
Right. So if f is non-negative on RD, then for any E which is Lebesgue measurable, so in the sense of chapter 1,
Mhm.
we can define a new measure of E as the integral f over E, where this is the Lebesgue integral. So the set of measurable sets for this measure mu now is just the same as the set of Lebesgue measurable sets. And so a sub-example, is that a word?
Yes.
Subexample is a word?
Yes, I
made
understand. It's a language is a agreement between the users. I perfectly understand what you mean.
Yeah. If you take 1 over the square root of pi, integral negative infinity to plus infinity, integral, I don't want to say negative. Integral over set e to the negative x squared dx. Now I'm going to assign a homework problem to show that this actually, if e is equal to r, it integrates up to 1. Then this is what we call the normal distribution with mean 0 and standard deviation equal to 1. Then, and here it's getting difficult for those of you of the statistician persuasion. In measure theory, mu of e is the measure. In statistics, mu is the mean. So if mu of e is this is the standard normal distribution. And that's a perfectly good measure. And it's also what's called a probability measure.
So, Professor, the definition of probability measure is the whole space integrates to 1, or is it possible to have different probability measures?
You can have different probability measures, but the main definition is that mu of x is equal to 1.
Oh, okay.
I mean, I'm going to give you another example here. Another sub-example. If you take mu of x, mu of e is the integral over e. This is now in 1 dimension. 1 over pi over 1 over 1 plus x squared dx. That's a probability measure. So if you look at what is mu of r in this case, this is 1 over pi times the arctangent of x between negative infinity and plus infinity, and that's just 1.
Right. This is a really good example.
Yeah, because you can compute it. It's
So, Professor, in the bottom of the page 263,
yeah.
Which part of the limiting property did he mention? It doesn't mean, like, he says that the counter additivity of mu follows from the usual additivity and the limiting properties of the integral. So which limiting property does it talk about? Is it the
It's monotone convergence.
Ah, okay. So that's page 107.
Yeah.
No, I'm sorry. That's page monotone. Okay.
Monotone convergence is the last one.
Ah, okay.
It's
The
the
last
second
one.
corollary of uh, Fatou's lemma.
Ah, okay. Page 62.
Yeah.
Mm. Or do we need that corollary 1.10 of the monotone conversion theorem because the summation and the integration interchange?
I don't think so.
Because the countable additivity means that change of the summation maybe.
Oh, okay. Yes, we need 1.10.
Okay.
Okay, so the next step is exterior measures.
Mhm.
Okay, it's the important part is if you have a space X, then an exterior measure is a map from the set of all subsets of X, so the power set of X, into the extended positive reals.
Mm.
So 0 to plus infinity. I want to say actually, if we go deeper into measure theory, which we don't have time for in this class, you can have also a thing which is called signed measures.
Oh.
So where the range of the measure of a set is actually between negative infinity and plus infinity, both ends included.
Mm.
But a signed measure is just the difference of two positive measures. We're just looking at positive measures.
Okay.
And the properties of an exterior measure is that the exterior measure of the empty set is 0. Secondly, it is monotonic. And thirdly, it is sigma sub additive. So if you have accountable collections of sets, then the exterior measure of the union of those sets is less than or equal to the sum of the exterior measures. Just like we had for the exterior measures in RD, where we had a description for that. And once you have an exterior measure, you can define the concept of measurability and basically say that a set E in X is measurable if and only if the exterior measure of A is equal to the exterior measure of A intersected E complement plus the exterior measure of A intersected E. And you remember that?
Yes.
back in the Blackboard days with classrooms, when we could all see each other, we actually showed that this is actually equivalent for the Lebesgue measure for our definition of measurability.
Mhm. The existence of open set that contains E such that
Yeah.
the difference is less than epsilon. Yeah.
So, and the main theorem of the section we read is theorem 1.1, which says the collection of measurable sets under this definition forms a sigma algebra.
Mm.
We did that already in the good old days with blackboards, right?
Yes.
Because we compared the two definitions and went along. And so we really don't have to do anything here.
Mm.
We've done this already.
Professor, I have a question actually. On page 266,
Yeah.
the inequality, the first inequality in the second formula, mu star of A is equal to that, and then less than equal to summation of mu star EJ, that part.
Yeah.
So I
Greater than
understand
equal.
that they say since G is greater than Gn, the complement changes the inclusion direction of the inclusion, so you get that
Yeah.
second term. But then the first term, Professor, because of the what is it?
What's the
third
first term?
property of the exterior measure, I think it's greater. But then, how come it's used in the lesser part?
Can you jot it down on my whiteboard? What do you mean, actually?
Oh yeah,
I'm-
sure.
I'm not quite sure where you are.
Oh, okay, no problem. So mu of A mu G N A plus right in the middle G and C.
Okay, that's the measurability of GN you use
Yes.
here. Right?
Measurability of A actually. Oh,
No,
yeah, GN. Yeah, GN.
Measurability of GN.
Yes, measurability of GN, and then that's a definition, and then this part is G intersect A. So I understand this part, but
Good,
I
yeah.
don't understand this part. But this part I don't know. I think this is greater. Because definition
Okay.
of GN is a union. Is it union or?
Okay, let me. If I put in J equals 1 to N, you okay with it? Then the
Oh yeah,
inequality still holds,
yeah. It holds.
and it holds for all N.
Yeah, holds for all N. But I don't know why that's the case, because GN, when you do the union, isn't the sum greater than the measure of GN?
Yes, it is.
So I think this part gives us a measure.
No, but you have to look at the whole thing. Just concentrate on this part, on the
Okay.
black underlined part. Look at the whole thing. We have for every N, mu star of A is greater than or equal the summation from J equals 1 to N of this thing
Mhm.
plus mu supper star of G complement intersected A. And that's true for any N, right?
I don't know.
No, it's true for any N. Because
But
the first thing is true for any N.
yeah, but isn't this equality is like this way?
Okay. But if I have the J equals 1 to N on the sum here,
Mm-hmm.
then the inequality is in the right direction, right? Because essentially,
Oh,
if
so if it
these,
is
if
any finite n, the equality is that
if
way?
it, the inequality is in the right direction,
Oh,
right? What you do is Gn complement, you make small actually, then this inequality holds for any n, right? It holds for any n.
I see. They show
Holds for
the derivation above, right above the part that we're reading. The
yeah.
paragraph above tells us that's equal. So it's actually it's the same thing. It's an equality. I see.
Yeah,
So
it
they're actually
ends up
equal.
it
Yeah.
ends up being equal because from if you look at the definition, the Carathéodory measurability definition, says mu star of A is equal to mu star intersected E plus mu star of A intersected. So this direction is obvious. It's always there.
Right.
And so all we have to prove is this direction to show equality. And that's what this does here.
Yes. Yes. I see it now, Professor. Yeah, I didn't quite make the link between the argument preceding this inequality. So
Yeah.
yeah.
So it essentially, in every single case, all we have to show is this direction in this inequality to show measurability. What just happened?
Oh.
You erased your stuff.
Oh yeah, I erased my stuff. I wanted to erase the other stuff, but then I can write it again.
No, that's okay. Angela is recording it.
Yes.
You know, you can't record.
Okay.
Okay. And so that's basically, that's the crux of theorem 1.1.
I have a question, Professor, on the very next sentence.
Yeah.
Our previous observation says that the sets of exterior measures 0 are Carathéodory measurable. So
yes.
Yeah. So where is that previous observation?
The previous
So, hello? Hello?
I'm back.
Oh, okay. So, Professor, did you get my question?
Yes, I did.
Oh, yeah, okay.
Uh, okay, so we want to show that if mu star of E is 0, then mu star, then E is measurable.
Uh-huh. E is in the M?
Yeah,
Mm.
E is measurable. That's what it means to be an M.
Mm-hmm.
So let A be an arbitrary set. So A is going to be A intersected E, not intersected, union A intersected E complement, right?
Yes.
So mu star of A intersected E, since A intersected E,
A
sorry,
subset of E? Mm.
no, right, is
So it should
contained
be
in
0.
E.
Uh-huh.
So this is 0.
Uh-huh.
And so mu star of A is greater than or equal to mu star
Oh,
of A intersected E plus mu star of A intersected E complement.
yes.
All right.
Mm-hmm.
A intersected E complement. And since the opposite inequality automatically holds, so since the less than or equal automatically holds by subadditivity,
Mm.
mu lower star A is going to be equal to mu star A intersected E plus mu star A intersected E complement. And this implies E is a subset, is contained in the sigma algebra, which means E is measurable.
Professor, how do you get this first inequality here? This one?
This one,
Yeah.
this inequality, by monotonicity of the exterior measure,
Mm.
right? A intersected E complement
Oh, that's right. That's right.
is
A
a
subset
subset
of
of A,
A
right?
as well. Yes, yes.
And this measure is 0.
Ah, we see. Okay. It's like an onion, step by step. We're peeling it off.
Maybe, yeah.
Okay. Ah, okay. Thank you, Professor. Oh my goodness.
It's not all that bad.
Yeah, it's not bad. Just takes forever to figure out if I don't have lecture. Trying to figure out by myself. It will take forever.
Okay, that was the reading assignment. I didn't assign any problems for today, right?
No.
Okay, for Monday. I'm gonna have problems.
Oh my goodness.
Exercises. Take
Uh-huh.
that back.
Okay.
1.2, which is metric exterior measures. And then we're gonna go exercises. Exercise. And 5.
Mm.
Now 5 in particular is a calculus exercise, so you shouldn't worry too much about it.
Okay, but it's multi-dimensional one.
So if there's one thing we should learn from calculus,
Mhm.
a higher dimensions is that it's all the same.
Mm.
Dimensions don't matter.
Okay.
If we understand what a derivative is, which
Yes.
we don't because we do it in one dimension and we do it always wrong. A derivative is
Linear operator.
right. If you look at this as a linear operator, then it's the same in all dimensions. Now
Yeah.
the fundamental theorem of calculus is a little different because it's different. It looks different in all dimensions, but it's still the same, saying that the integral of capital F over the whole space, no, lowercase f over the whole space is the integral over the boundary of the whole space of capital F. And if you look at this, where lowercase f is the derivative of capital F in whatever sense we define that.
Mm.
But that's, dimensions don't matter.
Okay.
Especially if you go above 4. Dimension 3 is a pain back.
Mm. Thanks for your affirmation.
Because 3 choose 1 is the same as 3 choose 2.
Mhm.
Which means I don't know how many of you did have 550. A 2 form looks like a vector.
Yeah.
Which is bad. Because then we have suddenly the vector product, V cross
Right.
U, right? Which
Mm.
is actually not a vector, but it's a 2 form.
Right.
And that's why dimension 3 is the worst possible dimension to live in, except for 2 and 1.
Yes.
Life would be lovely in 4 dimensions.
Yes. I think that's what God
Okay.
is love. He
What?
lives in the higher dimension.
Yeah.
He's living in the lovely space.
Yeah. No. I mean, even social distancing in 4 dimensions would be much easier than in 3. Think about it.
We go to the non-populated dimension.
Yeah. I mean, I think in 4 dimensions we would have very few pandemics. But okay. So I'll let you go for today. Stay safe. Have a nice weekend. And read section 1.2 and I will see you online on Monday, and then I will also post the final exam early next week.
Awesome.
Yes.
Thank you, Professor.
Okay.
Thank you, Professor. Thank you, Angela.
Have a
Yes,
nice
have a
evening.
nice weekend.
Thank you, Angela. Very helpful for this record.
Yes, very
Thank you,
helpful,
thank you.
Angela.
Yeah.